Hello everyone, this is Abhinav Garg from the computer science stream, and today I am going to present a presentation on for the switching theory and logic design assignment. The topic I was assigned was the XOR and the XNOR gate using minimum number of NOR gate. So starting the presentation with the introduction of a NOR gate. So a NOR gate is a logic gate which gives out a positive output only when both the inputs are low. For example, as we can see the truth table here, the output of the NOR gate is 1 only when the inputs are of A and B are 0 and 0. And when any one or both of the inputs gets equal to 1, the output becomes 0. The logic symbol for the NOR gate is shown here. A NOR gate is a universal gate. That means that we can design any gate with the help of NOR gates. Now, talking about the Boolean representation of the NOR gate, we can derive the Boolean representation of any gate with the help of a truth table. For example, here we can see the truth table of a NOR gate. Now, we know that using the sum of product form of the product terms only where the output equals to 1. So, from the truth table, we can write the Boolean expressions for the NOR gate as x equals to a complement dot b complement. Now this is one form of Boolean representation for the NOR gate. Now applying De Morgan's law on this equation, we can get x equals to a plus b complement. So these two are the Boolean representation of the NOR gates, and we are now going to use these to to design a XOR gates using NOR gate. Talking about XOR gate. A XOR gate is a digital logic gate that gives a true output when the number of true inputs is odd. The logic symbol for the XOR gate is as shown here. Now, looking into the truth table for a XOR gate, we can see that the output of a XOR gate is equals to 1 when the inputs are when the number of inputs when the number of true inputs are equals to 1. Now we can similarly derive the Boolean representation of a XOR gate, as we can see that the output of a XOR gate is only equals to 1 when A equals to 0 and B equals to 1, and another A equals to 1 and B equals to 0. So we can write the Boolean expression as x equals to A complement B plus B A dot B complement. This is one form of Boolean representation of a XOR gate. And now if we apply the distributive law on this equation, we can get that A equals to A complement B plus A dot A complement B plus B complement. Now again, if we apply the distributive law, let me show you with the annotations. We can see that we can apply distributive law on this part and this part. So applying this distributive law on this term, we can get A complement plus A dot B plus A, and then applying distributive law on this term, we can get A complement plus B complement dot B plus B complement. Now we know that A plus A complement equals to 1. So similarly, B plus B complement equals to 1. So we can say that x equals to A plus B dot A complement plus B complement. Now we can use this expression or Boolean expression to represent this expression in the form of NOR gates. Moving on to the next slide. In the previous slide, we have derived the expression for a XOR gate as x equals to A plus B dot A complement plus B complement. Now we are going to convert this expression in form of Boolean expressions for NOR gates. Now we know that the complement of A complements equals to A. Using that property, if we apply complement twice on this equation, its meaning will not change. So applying complement twice on this equation, we get the complement of A plus B dot A complement plus B complement and then its complement. So we get this expression as a result. And now if we apply De Morgan's law on this term. The, from De Morgan's law, we know that A dot B whole complement equals to A complement plus B complement. So we get A plus B complement plus A complement plus B complement of then its complement, and then the rest of the expression will remain as the last expression, and then we can apply De Morgan's law on A on this term A complement plus B complement's complement. So we get A A dot B, and then we can apply the distributive law on this whole term. So we get A plus B whole complement plus A, and then A plus B whole complement plus B, and then the rest of the equation will remain as the previous equation. And then again we can apply the De Morgan's law as taking one of the terms equals to this and the second terms equals to this, and then we get A plus B complement plus A and then its complement, then A plus B complement plus B and then its complement. And then again we can apply complement twice on this equation to get the below expression as a result. We can see that we can use this expression to represent a XOR gate using NOR gate, as A plus B complement can be calculated using one NOR gate. We can use the same result here, and then we can use the input, use a second NOR gate and apply A and A plus B complement to it, to its input to get this term, and use another NOR gate and apply B plus A plus B A plus B complement as an input, and then get this as a result. And then we can use another NOR gate and apply both and apply inputs equals to this term and this term to get this term, this whole term except the outer complement as a result. And then we know that if we apply same inputs to a NOR gate, it works as a NOT gate. So we can use we can give we can give inputs equals to this term, the term rather except the NOR gate to the NOR gate to get this expression. To be more clear, let's move on to the next slide where we have designed the circuit diagram. Now let's start drawing the circuit diagram for this expression. If we give A and B as inputs to this NOR gate, we get A plus B and then its whole complement. We can see these terms in the equation here and here. Now if we apply A plus B whole complement and A as input to this NOR gate, we can get this term A plus B whole complement and then whole complement. So we can see this term here in the equation. And then similarly, if we apply B as an input and then A plus B complement as an input to another NOR gate like this, we get B plus A plus B complement and then its whole complement as a result. And we can see this term in this equation here. Now if we apply both these terms, this term and this term, as an input to another NOR gate, we can get this expression. We can get this whole expression, and we can see this whole expression in the above the above equation here. This whole expression is the expression except the outer complement, and then we if apply this as an input to another NOR gate, we will get the result. So this is how we can get A XOR B. So here we have used 5 NOR gates to represent a XOR gate, and this is the minimum number of NOR gates which are required to represent a XOR gate. Moving on to the next slide, talking about the introduction of the XNOR gate, we can say that XNOR gate is a digital logic gate that gives a true output when the number of true inputs is even. The logic symbol for the XNOR gate is as shown here, and if we look into the truth table of XNOR gate, we can see that the output of XNOR gate is equals to 1 only when the true inputs are equals to even. Like in the first row, A equals to 0 and B equals to 0, the number of true inputs equals to 0, so the output equals to 1, and the last row, A equals to 1 and B equals to 1, the number of true inputs equals to 2, so the output equals to 1 again. Moving on to the next slide, we can talk about the Boolean representation of the XNOR gate. Similarly, like XOR gate and the NOR gate, by truth table. From the truth table, we can write the Boolean expression for the XNOR gate as y equals to a complement dot b complement plus a dot b. From the truth table, we can see that the output equals to 1 where a equals to 0 and b equals to 0. So we get a complement plus b complement as one term, and then output equals to 1 when a equals to 1 and b equals to 1. So we can get a into b as another term. Now this is one form of Boolean representation for XNOR gate. Applying distributive law on this equation, we can get y equals to a complement dot b complement plus a dot a complement dot b complement plus b. Now if we apply distributive law on both these terms, we can get a complement plus a dot b complement plus a complement plus b dot b complement plus b. Now as we know that a equals to a plus a complement equals to 1. Similarly, b plus b complement equals to 1. We can reduce this expression equals to y equals to a complement plus b dot a plus b complement. These both are the Boolean representation for the XNOR gate. Moving on to the next slide, we know that the Boolean representation of XNOR gate equals to y equals to a complement plus b dot a plus b complement. This expression we have derived in the previous slide. Now, XNOR gate is the complement of XOR gate. So if the output of XOR gate is x and the output of XNOR gate is y, so we can write y equals to x complement. Now using the equation for the XOR gate from this slide, this last equation, if we use this expression in y equals to x complement, using this value, we can say y equals to this expression. Now we know that the complement of a complement equals to a. So here the last two complements will cancel out each other. So y equals to this equation, and then this equation can be used to express XNOR gate in terms of NOR gates. We can see that a plus b complement can be shown with the help of one NOR gate by applying a and b as an input, and then if we apply a and a plus b component as an input to another NOR gate, we can get this term, and then b plus a plus b component as inputs to another NOR gate, we can get this term, and then if we apply this term and this term as an input to another NOR gate, we can get this term. So hereby we can represent XNOR gate with the help of 4 NOR gates. Moving on to the next slide, we have derived this expression for XNOR gate in the last slide. Now we can use this expression to draw the circuit diagram for an XNOR gate. If we give A and B as an input to a NOR gate, we can get A plus B complement as an output, and we can see this term here also. And then if we apply A and A plus B complement in another NOR gate, we can get A plus B complement, then this whole complement as output. And then if we apply B and A plus B complement as an input to another NOR gate, we can get this term as an output. And then if we apply this term and this term as an input to another NOR gate, we can get A XNOR B. This is what we wanted to derive. So we have designed both XOR and XNOR gate with the help of NORGates. We have used 5 NORGates to design XOR gate and 4 NORGates to design XNOR gate. Thank you very much.